All right. Before we dive back in, I just wanted to call out a special guest that we have here today beyond Spot, someone who's come from even farther away. And in fact, if any of you have taken CS50X, the open courseware version of the class, or dabbled in it over the past few years in some of CS50's online social communities, you might have had your questions answered by a certain human from New Zealand. And she's come all this way today to spend this lecture with us. This is CS50's own Brenda Anderson. If you might come up for acknowledgement from all of us here. It's not much, but just a little token of our thanks. Brenda has helped truly thousands of students online for the past many years. And in fact, her own daughter has been the artist behind the duck that's about to loom large in CS50 this year and beyond. So thank you to Brenda. All right, so it's hard to escape a discussion of artificial intelligence nowadays, but we thought we'd use this as an opportunity to connect some of these dots, because indeed, over the course of the semester, we'll not only be talking about artificial intelligence or AI, but really using it all the more constructively to help you solve problems, help you get unblocked when you hit a wall cognitively or syntactically when writing code. And indeed, it's no accident that we have this duck here looming large, which is really the embodiment of the sort of AI that you'll experience within CS50 itself this year. So let's talk about this so-called chatbot that inspired some of those headlines with which we began class that weren't quite on the nose. So the class will still be taught by us humans, but helped by this sort of CS50 duck, a chatbot of sorts. Now, what do I mean by this? Well, it turns out that when it comes to implementing something like an artificial intelligence, we don't quite have all of the building blocks yet, certainly after just today's week 0, to implement something like that. But I think we can sort of skate in that direction intellectually. So for instance, if we were to take a stab at implementing our own chat bot, some interactive text-based program that talks to us and answers questions and the like, we could try borrowing some of today's ideas already, those functions, conditionals, loops, and more. And I could write something like this. If I am writing code or pseudocode for a chatbot, I could program the chatbot to do something like this. If the student says hello to the chatbot, then the chatbot should say hello back. Else, if the student says goodbye, well, the chatbot should say goodbye back. Else, if the student asks how you are, the chatbot should say that it's well. But things get a little harder when you start asking more interesting questions, like, else if the student asks why 111 in binary is 7 in decimal. Now, you could imagine that we just have a conditional with this Boolean expression that programs the chatbot to just give you the answer and explain in an English sentence why that in fact is. But what if you, the student, asks why 110 is 6 in decimal, or why 010 is 2? I mean, you can just imagine the explosion in the amount of code that we would have to write to just anticipate every darn question that you might ask about today and every other class, not to mention all of the knowledge in the universe. So surely there are other ways to implement algorithms that allow something like a chatbot or AI more generally to be fed input still, like all of the internet, all of the World Wide Web, all of the pages and textual content therein, but to let it just figure out how to answer our questions based on those kinds of inputs, assuming the inputs themselves are accurate. So large language models is a term you might have heard bandied about over the past several months, or LLMs. And a large language model really is an implementation in software of code that actually takes as input lots and lots of language, like the text of lots and lots of web pages, dictionaries, encyclopedias, Wikipedias, and the like, and sort of infers from the patterns of English words or any human language what a typical human might actually say when asked a question. And some of these questions are easy, right? Probably on the internet alone, not to mention everyday life, if someone extends their hand and says, hi, how are you? Odds are, like with 90% probability, you're going to say, good, thanks, how are you? So I bet we could write software that just infers what it should say probabilistically, statistically, based on those kinds of patterns online. And that's indeed where the world is starting to go when it comes to the most sophisticated of algorithms, where you and I, the humans, we don't try to anticipate every possible input. Rather, we give it a more general purpose input, like all human knowledge, and ideally just let it figure things out. Now, we're not quite there yet, and odds are you've heard of hallucinations or just mistakes that these large language models make, but their inputs are imperfect. And sometimes there's a bit of randomness sprinkled in because you don't want the thing to always say the exact same thing. Even you and I might say, I'm not that great today 10% of the time. So you need to sort of perturb the output in some way. But within CS50, and within this world of large language models, we do have these tools like ChatGPT and Bing Chat and others. And we'll stipulate that for CS50's purposes, the direction we're going this year is that this is what's in the syllabus, ... That it will not be allowed, it will be considered not reasonable to use AI-based software other than CS50's own. So the goal here is not to simply take away tools that are clearly inevitable, in my view, and clearly helpful and productivity savers, but we'd like there to be some guardrails intellectually on just how helpful these chatbots are, because as you've probably seen, if you ask it a question, these chatbots are already pretty good at not just helping you finish your current thought, but it'll hand you your second and your third thought and sort of do the assignment for you. But I think through prompting, so to speak, we'll be able to coax some of our own tools, being computer scientists ourselves, in a direction that you actually find to be the right balance, akin to having a good tutor by your side 24/7 who doesn't just hand you answers, but indeed tries to lead you to the same. So you actually get something out of the experience. And ideally, 3+ months from now, those training wheels can come off too, and you're able to still stand on your own. So it will be reasonable to use CS50's own AI-based software, which will actually take the form of a CS50 duck, which is actually available now, and we'll use it throughout the term at cs50.ai, a web-based application that's quite similar to ChatGPT, but that has the personality of a CS50 teaching fellow, or TF, or teaching assistant TA, that also happens to think of itself as a duck. And for reasons we'll get to in a couple of weeks' time, but rubber ducks in particular are kind of a thing in programming. But more on that before long, as you can even see from the one there on my desk. With that said, too, allow me to call out CS50's own Brenda Anderson, whose daughter Sophie kindly not only created the first incarnation digitally of this duck, but also most recently, once it actually did more than quack a random number of times in response to questions, has now been virtually brought to life too. So all that and more over the coming weeks, but you'll find ultimately that the goal is to really bring to life the availability of an AI-based tutor that you have access to, a friend in your next to you, that will help guide you through a lot of the course's challenges along the way. And we've actually rolled it out this past summer already with some of your predecessors through the Harvard Summer School. One student wrote at summer's end that this duck felt like having a personal tutor. I love how AI bots will answer questions without ego and without judgment, generally entertaining even the stupidest of questions without treating them like they're stupid. It has, as one could expect, an inhuman level of patience. So there's actually something really there, because as many teachers as there are in CS50, myself, the course's preceptors, teaching fellows, teaching assistants, and course assistants, there's only so many of us, and we're only awake so many hours of the day. And I think you'll find, too, that we're on the cusp of something pretty remarkable in the coming years, where it's going to get a lot more enabling now to learn material, not only within the confines of a class, but on your own ultimately as well. And as one other student put it at summer's end with respect to the duck, love, love, love the duck, we're friends now. So that too awaits. But first, we're going to need to start with the basics. And we started today by talking about binary, and darn it, here it is again. So we can't actually get to the point of using or solving or implementing AI until we understand this. And odds are most of you won't know at a glance what this piece of software does, but these are the zeros and ones that represent perhaps the first program that any programmer writes, which is now a clue to some of you who have dabbled in code before. What does this pattern of zeros and ones tell a typical computer to do? Might someone guess? It's going to have it say hello world, which is one of the very first programs that most any programmer writes. Should you be able to recognize these zeros and ones? Do I recognize these zeros and ones? Like, no, not at all. I just happen to know that they are the same, and that was kind of a leading question. But they are representing data and instructions ultimately. Data like HELLO, comma, WORLD, and an instruction like print that data to the screen. As for what these patterns of zeros and ones are, this is not something that a computer scientist or programmer worries about. We just stipulate that, OK, someone somewhere knows how to do this. And it's probably someone like Intel who makes the hardware inside of the computers. But you and I, starting now, already in week 0, can start to view binary more abstractly. We don't care about the zeros and ones. We only care that you can use zeros and ones to represent more useful quantities like numbers and letters, colors, and more. So this, next week, is going to be the code we actually start writing at a keyboard. And this is that language called C. It's the same language I myself learned years ago when taking CS50, when all we learned at the time was C. But this, too, has some crypticness to it. And if you've never programmed before, you can probably wrap your mind around, OK, I'm guessing the printf prints out the hello world. But what's with the semicolon, the quotes, the \n, the curly braces, the hash include, and all of this stupid syntax? A lot of this in the beginning of any class is really a distraction. It is not intellectually interesting, but it's the stupid kind of stuff that's going to trip you up quite often. And so today what we'll do is focus not on syntax, characters on the keyboard, but ideas. Because what really matters in this program is that printf is a function here for our purposes. And that function is to display information on the screen. Everything else, as we'll soon see, has value and will be understood by you before long. But for now, it's a distraction. Let's focus on those building blocks. When it comes time to write code, though, for the curious, especially if you've programmed before, we'll use a very popular free and open source tool called Visual Studio Code, or VS Code. We'll use a cloud-based version of it that we pre-install everything you need in the cloud for you, so you don't have to deal with headaches like getting your Mac or PC to work. You'll use instead this URL, cs50.dev. But more on that in next week, week 1. For now, we'll use another cloud-based editor called Scratch. And odds are some number of you use this probably as early as like middle school or the like. And that was fine to create your own art, animations, games, interactive art, or the like. But we'll use it today for just a bit. And we'll use it in the course's first homework, aka problem set 0, to explore now some of these same ideas. And among the goals today, for the remainder of today, is not to focus so much on Scratch and the particulars, because this is not a language that you're going to use often, but to give you very visual representations of ideas so that when things do escalate next week to C, to the more cryptic, it's the same ideas just typed out instead of dragged and dropped. So by that, I mean this. I'm going to go ahead and share in just a moment the user interface of Scratch. But what's nice about Scratch is that this is how we're going to implement that same program today. These are 2 blocks or puzzle pieces on the screen, and they've been interconnected to tell the computer to say hello world on the screen. The user interface that we're about to use will look generally something like this. It's a web-based editor, though you can also download it locally to use offline. And you'll see that on the left here are a whole bunch of puzzle pieces or blocks. They're categorized by color, and the blue ones tend to relate to motion. For instance, the purple ones represent looks. The pink one represents sounds. The yellow one represents events. More on that soon. The orange ones represent control. And then there's operators, variables, my blocks, and even some extensions we can install as well. So it just categorizes things visually and colorfully so that you can sort of find what you're looking for. But we're going to use these puzzle pieces to drag and drop them onto this area here. And we're going to connect them when we want them to do something. What can they do? Well, by default, Scratch comes with this cat here, otherwise known as a sprite, which is a character in a game or in a graphics context. And this cat lives in this 2-dimensional world in which the cat can go up, down, left, right. And you can actually change the cat's costume to be a dog or a bird or anything else. It really is more of an idea than it is a specific animal in this case. But the world that Scratch lives in looks a little something like this. It's like a Cartesian plane with x coordinates and y coordinates. And the numbers don't so much matter fundamentally, except that when you want the cat or any character to go up, down, left, or right by some amount, it's useful to know, for instance, that 0, 0 is the middle, 0, 0 for x, y. All the way up is a y value of 180. All the way down is negative 180. All the way to the left is negative 240. All the way to the right is 240. And generally, you're not going to have to worry about numbers. You're going to use these relatively. Go right, go left, go up or down. But that's just the world that Scratch itself lives in here. So let's go about using Scratch here. I'm going to change over to my cloud-based editor here, where I've gone to scratch.mit.edu, and I've clicked Create in order to create a project. And that gives me this blank canvas here. And I'm going to do these somewhat quickly, because I kind of know what I'm looking for. But part of the process with problem set 0 is just going to be clicking and dragging and sort of scrolling around to see what building blocks exist. But I know under Events, there's this puzzle piece here, when green flag clicked. Why is that germane? Well, if I zoom out and go back to Scratch's world at the right here, notice that above Scratch's world, there's a green flag, which is going to mean go, and a red stop sign, which of course is going to mean stop. So if I drag this puzzle piece anywhere into the middle, it's just going to plop where I put it. But what that means semantically is when someone clicks that green flag, I want Scratch, the cat, to do this other thing. Well, what do I want it to do? Well, let me go under looks. And looks here in purple have some puzzle pieces like this. Well, I can say hello for some number of seconds, or I can just go ahead and say hello. So let's do that. I'm going to drag this say block. And notice that as soon as I get close enough, it's going to sort of magnetically want to connect. So I can let go, and they snap together automatically because they're the right shape. I don't have to say hello exclamation point. I can change it to the more canonical hello, comma, world. So anything in this white oval is editable that you can change as just text there. If I now zoom out, let me go ahead and click the green flag. And voila, this should be my first program in Scratch. Hello world. Without any of the distractions of syntax or weird characters on the screen, it's just done what I want it to do. All right, let me go ahead and click stop there. And let me make it a little more connected to what we've discussed thus far. So this puzzle piece here, say hello world, represents what type of building block using the vocabulary of today? So it's a function. So these purple blocks are functions, say hello world. And let me give you another piece of terminology. These white ovals that take textual input, in general, those are called parameters or arguments. And they customize the behavior of a function. So a parameter or an argument customizes, modifies the default behavior of a function, like in this case, say. Similarly, in the C code from earlier that we'll see next week, the printf function took a quoted phrase like hello world similarly as input. But more on that in the future. So how does this connect to what the mental model we presented earlier? Well, here's problem solving, as I described it earlier, inputs to outputs with algorithms or code in the middle. Well, what we've got here really is an input of hello world, the white oval. The function or algorithm that it's going into as input is the say block. And what is the output of using this say block, the say function? It's the visual effect of having the cat have the little speech bubble appear above its head saying hello world. So everything we do, in fact, can be mapped back to that very simple idea of inputs and outputs. Well, let's make it a little more interesting, though. It's a little boring to just say hello world all the time. Let me go ahead and drag this away. And if you just drag it to the left and let go, it gets automatically deleted. Let me go under sensing in light blue here. And you'll see there's a bunch of blocks, one of which is an ask block, an ask function, which is going to prompt the human, me, for some input. So let me go ahead and drag that over here. And it snaps together. I could change the question, but I'm OK with that question. We'll use what's your name. But notice that this block, ask, is a little special. It is not just going to display like a speech bubble on the screen. It's actually going to return a value. And this is another term of art today and onward. A return value is some value that can be handed back to you conceptually from a function so that you can do something with it. It's as though the ask function asks someone for their name, writes it down on a piece of paper, and hands you the piece of paper. You can do anything now that you want with that name. And here is how you access the name in this special block called answer, which again, we'll start calling a return value. So if I want to say hello to someone specific, I'm going to do this. Let me zoom out. Let me go back to looks. And let me go back to say. And I'm going to change the say block here to hello, comma. Then I'm going to zoom out. Well, I need two inputs, I think. So all right, I'm going to grab another say block, and I'm going to put it below. And I could just type David, but this is going to defeat the whole point of asking me for the name, and it will only work for me. So I don't want to do that. So let me go back to sensing. And notice the shape is important here. Even if it's not quite the same size, the shape matters. And I can actually drag this and change the input of this say function to be whatever that return value is, that piece of paper that has the person's name on it. And it grows to fill. But now we have a program that I think, when I click the green flag, watch, is going to prompt me, what's your name? And now I have room to type down here. So I'm going to type DAVID. I'm going to hit enter, and it should say, hello, Dave. Wait, Oh, maybe maybe it was, didn't work. DAVID. Here we go. Hello, David. It's missing the hello. But I'm quite sure we have a hello right there. So what explains this bug or mistake? Yeah. Exactly. It's just, put another way, my Mac, my PC is just so darn fast that it did exactly what it was supposed to, but it said, hello, David, so fast that we didn't even see, we being the human, the slowest part of the puzzle, see the actual hello. So there's a few different ways to fix this. As you know, we could have it say hello for some number of seconds. So I could kind of do that. So let me do this. I can decouple these by just dragging and letting it go so that they're magnetically far apart. Let me go ahead and drag this one, say hello for 2 seconds. I'm going to change the grammar here to be hello, comma again. I'm going to go ahead and disconnect these two. I'm going to throw away the old one that I don't want to use. And I'm going to reconnect this so that now, OK, it's going to say hello for 2 seconds and then my name, hopefully. So let me click stop and start. DAVID, enter. OK, so it's better, but it's kind of like poorly implemented. Like, come on, I just wanted to say hello, comma, David. Why is that hard? Well, maybe we can actually combine these a little differently. And let me propose this. Let me actually get rid of these blocks again. And let me go ahead and just say one thing. But can I somehow combine this to say hello, comma, David, all in one breath? Well, it turns out if I go under operators, I know from having played with this before that there's this puzzle piece down here called join. And it's a circle, or it's an oval. It's a little big, but again, it will grow to fill. And by default, it wants to join 2 words, apple and banana. But whoops, but those are just placeholders. So let me go ahead and drag this over the default hello. Let me change apple to hello, comma, space. And then banana, let me go back to sensing. Let me grab answer and drag and drop that. So now notice that I'm kind of layering my ideas. And put another way, the output of this join block is presumably going to join 2 things together, apple and banana, or hello, comma, David. And then the output of join is going to become the input to say. So aesthetically, it just looks better. It's still correct, but it's just better. So if I type David and hit enter, hello, David. This is what a normal program would presumably do, not show you part of the phrase and then the rest of the phrase. Like, it's just better in this way. So let's connect this now to this same puzzle piece and this methodology. So here's that same puzzle piece. Ask, how do we fit it into this input and output flow with algorithms? Well, the input to that puzzle piece is something like, what's your name? Question mark. Then the algorithm or the code implementation thereof is this ask block and wait. So the human has a moment to type their response in. The output of that function, recall, is a return value. You don't see anything on the screen by default because we've not used say yet. But we get this return value. And let me scooch everything over now so that we can now join those inputs together. So here's this puzzle piece. Let me go ahead and propose that the inputs now to the join block are 2 arguments or 2 parameters, so to speak, hello and answer. They go into that join puzzle piece whose purpose in life is to return 1 joined version thereof. Let me slide this all over logically now so that now that output becomes the input to the say block. And now is why the cat has the speech bubble saying all at once, hello, comma, David. So what we've done here is kind of composed the output and from one function into the input of another. And you can think of this in a couple of different ways, left to right as I did there. We're kind of like stacking these things on top of one another. But at the end of the day, even as programming gets more and more powerful for us, it's just inputs and outputs, inputs and outputs. And thankfully, with built-in functionality from our friends at MIT who designed Scratch, I can even do something playful like this. I can go to that extensions button at the bottom. And there's a lot of fancy things I can add here, like text to speech. So let me go ahead and choose text to speech. And let me go ahead here and change the say block in purple. Let me get rid of the say block. And let me borrow this. Let me get the speak block like this. And now let me drag and drop this oval. It's going to grow to fill. And I think it's just about to be a little more interesting. Let me click play now. And hopefully this isn't too loud. DAVID, enter.
Hello, David.
OK. Thank you. Thank you. That's a low bar. Let me go ahead and set the voice too. And you might now remember how we began class where we had a robotic computerized voice. Well, we didn't use Scratch at the time, but we could change this in Scratch alone to be a little different. So DAVID.
Hello, David.
OK, a little creepy, but we can play all day long with that. But the point is that these functions are just now doing something a little different, but it's just these inputs and outputs. Well, let's make the cat more like a cat. Let me go ahead and throw away all of this asking questions stuff. Let me go up to sound, and let me go ahead and drag the play sound meow until done. And here, too, it comes with meow. You can add your own sounds as well, but I'm just going to use the default meow. And here, too, hopefully this won't be too loud. Let's make the cat meow by clicking play. OK, it's a little piercing, but it's cute. And if I want the cat to meow twice, I could just play the game twice. All right, but it would be nice to just get it to meow automatically 2 or 3 or more times. So you know what I could do? I could just drag a second one of these. I could actually, you know what? I could even just right click or control click and duplicate them. But I'll just keep dragging and dropping. There's different ways to solve problems. And now let me click play. OK, cat does not sound particularly happy. So we could go under, how about control? We can wait 1 second. Now there's no room, but it will sort of expand to give room for me. So let me try this. And now it's going to wait 1 second in between meows. OK, let me stipulate that is correct. If my goal was to get the cat to meow 3 times, it meowed 3 times. But per our discussion earlier of algorithms and the design thereof, this is not the best design. OK, thank you for playing along at home. Yeah. In what sense is this arguably not well designed? Yeah. I repeated myself, which actually in programming tends not to be a good thing. Now, it was easy. I almost resorted to copy paste, which saves me time up front. But just imagine a contrived scenario now. What if I wanted to wait like 2 seconds in between? All right, it's not that big a deal. I change it here, and I change it here. But what if the program is meant to meow 10 times? Then I have to change it here, and here, and here, and here, and here. And eventually, I'm going to screw up. Like, humans are fallible. I'm going to overlook one of them. One time, it's going to be 1 second. Another is going to be 2. And just stupid things will happen. You're setting yourself up for failure if you design things poorly. And so I would propose that we use another type of building block to solve this instead. Yeah. Yeah, so we could use a loop and just write minimal code, but to accomplish even more functionality. So let me throw away most of these blocks. And let's go and grab this repeat block, which we haven't used yet, but it's right there. And as the name suggests, this will allow me to repeat something some number of times. Let me put these 2 puzzle pieces inside. It'll grow to fill. Let me reconnect it to the green flag. I'll change the default 10 to a 3. And now it's just sort of better. Because if now you want it to meow more times, you change it 1 place. If you want it to slow down, you change it in 1 place. There's no room for error. And that's generally a good thing. But you know, this is silly. Like, Scratch comes with a cat. Why didn't MIT give us a puzzle piece called meow? Like, why am I implementing the idea of meowing myself? Like, that took me, what, 1, 2, 3, 4 puzzle pieces. Why isn't there just 1 puzzle piece that meows for me? This, too, we can do in code, be it in Scratch or C or other languages, too. I'm going to go down to these pink my blocks here, where I can create my own puzzle piece. And I'm going to call this literally meow. And I'm going to go ahead and just click OK. And notice that it's given me this new type of start connector. It's a start puzzle piece that nothing goes above it, but you can put anything you want below it. And I'm going to go ahead and cheat here. I'm just going to grab my existing code, so to speak. This is code I'm writing, even though it's puzzle pieces. And now let me just claim, and I'll move this aside, here is now an implementation of my own function, my own block called meow, whose purpose in life is to meow until done and then wait 1 second. But what's powerful now is notice at top left, now that I've made the block, I can use it any number of times. So I can grab this meow block, drag it over here. And you know what? Now that meow exists as an idea, I can abstract that away. And I'm just going to arbitrarily drag it way to the bottom. I'm not deleting it. I'm just putting it out of sight, out of mind, so that we can focus now on this idea. And I claim that this implementation of meowing is sort of better because it's more compact, it does what it says, and I don't care about the implementation details of meow. So this idea of abstraction, something we're going to use frequently. To abstract something away is to simplify. Don't think about the underlying implementation details. Just care about what it does or what it's called. Someone has to care about the implementation details, like me 30 seconds ago. But here on out, I don't need to care. And so in fact, you and I are using the abstraction that is Scratch, because I don't know how to put a speech bubble on the screen. I don't know how to create that sound meow. MIT did that, and they abstracted those pieces of functionality away already for us by just giving us these puzzle pieces we see here. So the code will work the exact same, but it's sort of better designed now, because now I've abstracted away the idea of meowing, but I bet I can improve this further. Can I get rid of the repeat block altogether? And let me just tell the meow block how many times to meow. Well, let me go down to the bottom and look at the implementation details. I'm going to right click or control click on this, and I'm going to edit it. So I'm going to make a change. And I didn't do this before, but I'm going to call it meow as before. I'm going to add an input. And just so I know what it says what it does, I'm going to add the word times here. So, and I'm going to change this placeholder to n for number is the go-to placeholder anytime we want to talk about a number in CS. So now notice the puzzle piece looks a little different. It takes an argument or a parameter called n, which represents the number of times you want the thing to meow. Now, that doesn't do that yet. So let me go back to my other code. Let me just decouple these temporarily. I'm going to move my loop into my implementation of meowing. But I don't want to hard code, that is, literally write the number 3 anymore. I'm going to grab this circle, this oval, and put it there. So now I've generalized the function. So now it will meow any number of times, 0 on up, by executing that loop. And now, more powerfully, out of sight, out of mind, notice that my code just became so darn simple. Like my function is called meow. It meows some number of times. All I have to do is type a number there, and it just works. And I don't care anymore about those lower level, so to speak, implementation details. So here, no surprise, if I type in the number 3, zoom out, and hit play, it still works just fine. So any questions on what we've just done here? It's still just meowing, but that's besides the point. It's this creation of our own functions, this modularity, this abstraction, that's going to be the idea that keeps coming back to us. Questions on any of this? No? All right. So let's make this a little more cat-like. Let me throw away all of this code, and let me go ahead. Oops, let me throw away this code first, and then the rest of this code. And let me go ahead and give myself another green flag block. And let me go ahead and let's create a cat that allows us to pet it by moving my cursor over the cat. And maybe it likes that, so it'll meow when I do that. So let me go under control. And let me grab this if conditional, which we talked about as a building block earlier. Let me go to sensing. And we haven't used this before, but here is a weird sort of diagonal shape that says touching mouse pointer question mark. So that's a Boolean expression. So I'm going to drag that. And it's definitely the wrong size, but it is the right shape. So it will grow to fill. And the question I want to ask is, if the cat is touching the mouse pointer, then go ahead and meow happily. So let me grab the meow sound, put it in there. And so I think when I click the green flag to start the program, and now I let the cursor, the mouse pointer, touch the cat, we should hear. Doesn't seem to be working. There's a bug or a mistake in this program too. What did I do wrong? Yeah. It didn't specify what? I don't need to specify the sprite explicitly because, a detail I didn't discuss earlier, in the bottom right of the screen, notice that the cat is already selected. So this code relates to that cat. So your instinct is good if we had 2 or more sprites, but I just have 1. So I'm covered there. Other thoughts? Yeah? It only checks once. So I click the green flag. The computer did what I told it to do. The mouse pointer was not touching the cat at that moment because it was touching the green flag. So of course it didn't meow. So what maybe is the fix here? What puzzle piece can we add?
After the green flag is clicked, have it wait 5 seconds or 10 seconds.
OK. So OK, interesting solution. So let me go ahead and under control, let me grab a wait 1 second. I'm going to change the 1 to 5. And now I'm going to click the green flag. So here we go. 1, 2, 3, 4, 5. Damn it. OK, that was yours, not mine. It didn't work. Sorry? Oh, maybe forever. So your approach would work, but it's very much a hack, if you will. Like I would have to time it perfectly so that the mouse pointer is touching it, or conversely, I have to drag it there and just leave it there for 5 seconds. And that's a little weird, because like you don't just touch a cat and then like 5 seconds later it meows at you. Like presumably we want it to be more interactive. So I like this idea of a loop, right? Why don't we just tell the cat to forever listen for the cursor, as by using not repeat, but forever. Let me move this in here. So now the cat's going to be told when the green flag is clicked, just forever, if touching, if touching, if touching. Oh, meow when actually touched. So now if I zoom out and hit play, nothing's happening. I don't have to wait any number of seconds. But when I do touch the cat, fan section here. Thank you. So now it's actually working quite well. So there we have sort of a logical bug, but it does make sense if you think about what it was you told the computer to actually do. Well, let's make things even more interesting by using one of these extensions. In this bottom left corner, this is how I got to text-to-speech earlier. Let me go to video sensing over here too. And I can actually, there we go, literally the video has come on. Let me go ahead and do this. Get rid of this code. And let me step out of the frame. When video motion is greater than, well, this is CS50, so let's just type in 50, which is just a measure of motion. Let me go and play sound meow. OK, and let me stop and restart. All right, so there's the cat. OK, it worked. The cat's a little insensitive. There we go. Actually, you know what? Maybe it's just, well, let me put, let's change it to 20. Oh my gosh. Oh, that's OK. There we go. All right. There we go. So now it's a little more sensitive to the petting by using the camera. Now, this is kind of a weird example. And if I just start moving around crazily, like it's just going to meow incessantly, which is what was happening. OK, when in doubt, this is when you reload the page. All right, so now we're back to where we wanted to be. But where can we now use these kinds of building blocks? Like we were doing such tiny little programs. But even that, like we could turn into a whole game, I bet. Could we get like one volunteer to come on up? One volunteer? Everyone's like looking down. How about, OK, on the end here. Come on down. Yeah. All right, round of applause for our one brave volunteer here. All right. These Super Mario cookies are on the line for you, depending on how this goes. So I'm going to have you come over here. And in advance, on Scratch's website, we have some pre-made games, one of them written by one of your predecessors, a former student, that they implemented this sort of whack-a-mole game. So what you're about to see is the camera turn on you. And you're going to see 4 moles, above, below, left, and right. And using only your head, up, down, left, right, the goal is to whack a mole to get a point every time your head touches one of these sprites. So you're about to see things get very interesting very quickly. But using these building blocks, just those simple blocks, but have 4 sprites, not 4 cats, but 4 moles in this case, we can actually turn these into actual games. So here we go. The beginner. OK. And we just need you to center your head first. Nice. 10 seconds. Nice. 2 seconds. All right, a round of applause. Thank you. Do you want to introduce yourself?
Hi, everybody. My name is Vanilla. I'm a first year, and I'm going to be majoring in computer science and economics.
Nice to meet you. Here we go. Thank you. So we won't look at the code for that actual game. It was written by one of your predecessors, and you can see it online if curious. But you can think about now with our functions, conditionals, Boolean expressions, loops, how you could kind of compose that kind of program. So odds are there was a loop that was just constantly listening for that kind of connectivity, or it was one of those extensions that was waiting for motion to go touch one of those sprites. Notice that there's these numbers up here, and we haven't talked about this yet, but just like in math, where you can have variables, x and y and z, in programming, you can create variables. using other puzzle pieces in Scratch that just keep track of how many seconds are left, that keeps track of how many times her head hit one of the moles. And so you can implement the mechanics of games using very simple building blocks. But how do you go about building something that's more interesting and interactive like that? Let me go ahead and bring up, for instance, one of the very first things I wrote years ago when I was in graduate school, and Scratch had just come out. I was taking a class at MIT's Media Lab, and they invited us to beta test, that is, try out the software before it then became part of the world. And the game I made was this one here. Let me find the right version of Oscar Time. So Oscar Time is a game that took me tens of hours probably in the end. It was a little bit addictive, but let me go ahead and full screen it. And I won't play the whole game, but it looked a little something like this. Where trash is falling from the sky. And I can click on it and drag it. And notice as I get close, the lid opens up like this. And if I let it keep falling, it goes in, and Oscar gives me a point. And I can do this again.
If you really want to see something trashy,
all right, here comes something else.
I have here a sneaker that's
so now there's two pieces of trash.
It's all full of holes and the laces are
and it just keeps going and going and going. And if you can lower the volume for just a moment, we'll let more trash fall. But to your comment earlier about one sprite or more sprites, that's what we're seeing here. Even though our examples thus far are just one pack, one or two puzzle pieces, or a few puzzle pieces, here is, I claim, a sprite. Here is another sprite. Here is another sprite. And by toggling among them in that bottom right-hand corner, I can just associate different puzzle pieces with each of these sprites. Now, I didn't start off by implementing this whole game. And in just a moment, if we can raise the volume a little bit, we'll see even more trash is falling. So this is why I hate this song now. Like, I have 10 plus hours listening to this song on loop just to get the timing right. But it brings to life all of these different sprites. And if you play it again and again, it's always a little bit different because I'm using some randomness. So this newspaper doesn't always fall from there. Sometimes it's here, sometimes it's here. And so here again, we have mechanics of a game where things are being perturbed a little, randomized a little bit to keep things more interesting. And let me go ahead. There we go. How about raise a little volume? One more piece of trash. So a clock, it just goes on forever, this kind of game. But let's go ahead and consider, let me close that. Let me go ahead and consider how I went about implementing that from the get-go. So I will stipulate, let me open a few of these versions here, that the very first thing I did was pretty much just implement the stage, right? I was kind of procrastinating, so I poked around, I found the Sesame Street lamppost, and I like dragged it into the world, and done. Version 1 is done. It didn't do anything, but at least I had the world sort of laid out. That is to say, I took a baby step toward my goal. Then I started thinking about, all right, how do I bring the trash to life, even if it doesn't do much of anything else? And so I created another sprite by clicking the appropriate button in that bottom right-hand corner, and I thought about, well, what do I want this trash to do? I want it to just kind of fall from the sky. And so what I did here was the following. If I go to this trash piece here, or actually, sorry, out of order. What I actually did first was I didn't even have the trash fall. If I play this game, the trash just stays there in the air. But I can do this. I can drag it. And as before, as I touch the other sprite, I get the trash can lid to go up. So how do I do that? Well, let me click on Oscar down there, my first sprite. And here are the puzzle pieces via which I implemented this idea. I changed Oscar's costume, his appearance, to be just number 1, which was one of the images I imported into the program. And then I forever did this. If Oscar is touching the mouse pointer, then change Oscar's costume to number 2. Otherwise, change it back to 1. So it's super simple animation. I'm just toggling between lid up, lid down, lid up, lid down, but it kind of feels interactive. And if I wanted to really make this pretty, I could have like 30 different costumes where the lid is ever so slightly higher. Then it would look even more like a movie or fluid motion. But this was enough to get the job done. Which is to say, I didn't try to implement all of Oscar Time together. I just took a second baby step toward my goal. And then my next version of Oscar Time might have looked a little something like this, where now the trash, there's more going on here. Let's look at 2 of these blocks of code. The first thing I did was I enabled drag mode to draggable. And I had to Google to figure this out, because otherwise it didn't let me drag the trash while playing the game. But once I figured that out, I tell the trash to go to a random x coordinate between 0 and 240 from left to right. And then the y location 180, because I always want the trash falling from the sky. And then what do? I told the trash to forever change its y coordinate, its vertical coordinate, by -1, -1, -1, so like 1 pixel at a time, which creates the illusion of it falling from the sky. But I needed to do one other thing, and let me scroll up. Each of your sprites can have multiple programs, multiple scripts, so to speak, that are not attached to one another. They will happen in parallel for you. The second one is saying this: forever, if the trash is touching Oscar, what should it do? Go to a completely different x and y location at the very top. Why? Well, as soon as I drag the trash over the Oscar, I want it to disappear as though it's going into the can, and I then want it to reappear at the top, so more trash falls. So I just thought about, like, what would it mean for the trash to go into the trash can? Well, who cares? What really matters to the human user is that it just disappears and teleports elsewhere. And so that's the idea I implemented here. So if you can reduce sort of intuitive ideas to just basic building blocks like this, you can start to make things much more interactive. And lastly, if I look at this version here, you'll see that we've combined these. And so indeed, if I actually go ahead and play this now, not only is it falling, I can let it fall right on top of Oscar and watch it disappear. But notice, Oscar doesn't pop out yet because that was the 4th version, and then the 5th version. And then I added the annoying music and so forth, but sort of compose this program step by step by step so as to accomplish my larger goal. And this is going to be true of all of the code you write, be it in Scratch or C or Python or the like, trying to come up with, or rather trying to reduce your ideas, your grand vision, to just baby steps, building blocks, so that you start with version 1 and maybe you submit version 10 or 20. But you don't try to implement version 10 or 20 at the get-go. You take those incremental steps. All right, how about one other? Well, let me propose this. Let me go ahead and open 3 games that represent one that your predecessors also implemented, which looks a little something like this in version 0. Suppose I wanted to implement a game that simply has these kinds of mechanics. I'm touching my arrow keys on my keyboard, up, down, left, and right, and I'm moving the Harvard logo. Let me zoom in a bit. So if I hit the up arrow, the Harvard shield goes up. If I hit the down arrow, the shield goes down. If I go all the way to the left, it goes left until it hits the wall, and same thing on the right. So this is like the beginnings of a game or a beginning of a maze, something like that. Well, how might I implement this? Well, let me look inside this one. And there's a lot going on. But again, I sort of took simple steps. Notice that I've got 3 sprites: a left wall, which is just a straight line, the right wall, which is a straight line. And just intuitively, why did I implement those as sprites? Why do they need to exist as entities themselves? Yeah, in front. Yeah, I want it to interact with the shield, so I need to be able to ask that Boolean expression, like not touching mouse pointer, but touching shield, for instance, a different type of yes/no question. And so what is the code for the shield actually doing? Well, there's a lot of duplication, and let me focus on the abstraction first. Notice that I've got this one green flag clicked. I want the shield to go dead center, 0, 0, and then forever listen for the human's keyboard and feel for the wall. So I decided to implement my own pink puzzle pieces that implemented 2 separate ideas. One, just listen for the keyboard, up, down, left, right, and then do something. And then feel for walls is this idea of whenever I go up, down, left, or right, if I touch a wall, I need to stop doing whatever the keystrokes are telling me to do. So now if we dive into those implementation details, listen and feel are abstractions, custom puzzle pieces. Let's look at the implementation details. Well, here's the keyboard. If the key arrow up is pressed, change y by 1. If key down arrow is pressed, change y by -1. And you can probably see where this is going. Right arrow is x by 1. Left arrow is x by -1. And that's sort of all that's involved with up, down, left, right. But wait a minute. Why is there no loop in this listen for keyboard puzzle piece? I needed a loop last time, so it constantly works. Exactly. I put the loop in my main part of my program up top, so something is telling me to keep listening again and again. So it's got to be somewhere, but it doesn't have to be in the actual implementation. And lastly, how about this feel for walls? Well, if touching left wall, which is just another sprite, change x by 1. So that is to say, if I'm touching the left wall, I want to kind of bounce it back the other direction. And same thing on the right wall. If I'm touching the right wall, I want to bounce it back to the left, which effectively means that even if the human's hitting the key, it's like fighting with this code, but it's never going to go through the wall based on that math. It's going to stop it right there. All right, let's add something else to the mix. Suppose I want the game to change to be a little something like this, where Yale is some kind of block in between me and like the exit. So some dramatic, race here. OK, I just got by. But the Yale logo doesn't seem to be doing all that much except bouncing. So I'm guessing there's a loop, maybe a conditional, like checking for those walls too. So let's go ahead and zoom out, see inside. Let's not worry about Harvard, because it's pretty much the same. Let's look at the Yale puzzle pieces. And sure enough, go to the middle, 0, 0, point in direction 90, so point horizontally on the grid. And then if touching left wall or touching right wall, I'm kind of cheating this time, but cleverly, just spin around and do 180, so you effectively bounce off the wall. This just tightened up my code. I don't need to do the -1 or the +1. I just say bounce in this form of code. Otherwise, just constantly move one step. Now, if this is a game where Yale is supposed to be better and faster, well, let's change the 1 to 5. Move 5 pixels at a time. Let's move it 10 back and forth. Let's maybe 100. Uh-oh. So what just happened? That is a bug, which we can avoid by just not doing that. But why did it break out of the wall? Yeah. Exactly. Because I'm doing 100 steps at a time, I'm never actually touching the other sprite, because I'm sort of stepping way over it. So there's never a moment where they're actually touching. So previously, I was just getting lucky by doing fewer steps, because it's gradually going over the wall, which gives me just enough time to detect as much. So I would have to kind of tinker and handle this a little bit differently. So it's a bug if it's too fast. But at least if I keep it slow and reasonable, the math actually does work out, so long as it starts again in the middle. Well, let's do one final flourish here, whereby let's bring MIT into the mix, right? They're super smart, so maybe they can kind of track us and follow wherever I'm going. So how might this work? All right, so nothing happens yet, because we haven't finished composing the game. And notice here, OK, now MIT is struggling. Like, it's kind of twitching there, because it's going just above, then below, and then above and below. So we could fix that too if we want. But that's just a function of my math, 1 pixel at a time. Let me open up this one, see inside, and click on MIT. And it doesn't take much to implement MIT, it seems. So go to random position, forever point towards the Harvard logo outline, AKA the shield, and then move 1 step. So if I wanted to make MIT even smarter, even faster, what do I change here? Yeah, change 1 step to like 2 steps to double their speed, or 5 steps, 10 steps, or 100 steps, and the game's going to be over like that. But that's all it takes to now make these kinds of elements. So if you are a game player on your phone or consoles or computer or whatever, if you think about almost any game, you can probably now start to think about how they implemented those mechanics, because it's just being reduced to functions, conditionals, loops, variables, and the like in this case. So let's go ahead here and have maybe one final volunteer. We've got one more bag of Oreos here. OK, that was super fast. Do you want to come on up? All right, brave volunteer, come on up. All right, let me find the full-fledged version of this that one of your predecessors made. And let me get the right one. OK, here we go. We'll see some instructions on the screen in just a moment. And when we hit play, you'll see that the mechanics are all combined now into one full-fledged game. But first, an introduction. It's on.
Hi, everyone. I'm Sam. I live in Apricot. I'm a freshman, and I'm from Nepal.
All right, welcome to the stage. All right, so here we go. Yep, go ahead and click the green flag. So you see the grid is just bigger this time. Nice. Now there's that Yale element. OK, third Yale. All started at slightly different positions. Nice. All right, there's MIT. Oh. Got to go fast. Oh. No. Nice. No more walls, but 2 MITs. Princeton now. Second to last level. Oh. All right, clearer. There we go. Nice. A few more lives. Oh. There we go. There we go. All right, a couple more tries. Yes. Oh, no. I'm sure it's getting stressful. All right, one more try. All right, a round of applause nonetheless. Nicely done. Thank you. So, as you might have noticed, if your eyes started to wander to the light bulbs here, there's actually 64 of these light bulbs. And I'm wondering if you divide 64 by 8, that's 8 bytes of light bulbs. And we now have some Unicode in our vocabulary. So might very well be the case that we've been spelling something out on the stage here for you all of this time. But before we adjourn for cake to be served in the transcript, allow me to introduce some of CS50's human friends, the Harvard Crocodillos and the Radcliffe Pitches, to give us this exciting ending. This is CS50.
There's a certain someone who I'm indebted to, and since you'll be in CS50, I have this friend for you.
2, 3, 4.
Oh, Rubber Ducky, you're the one. You make these sets so much fun. Rubber Ducky, I'm awfully fond of you. Rubber Ducky, you make me smile, and you help my code compile. Rubber Ducky, you're my very best friend, it's true. When I'm at a standstill, your debugging abilities stun me. When I'm at the end of my rope, you just snap and my code's up and running. Rubber Ducky, you're so fine, and I'm lucky that you're mine. Rubber Ducky, you're my very best friend, it's true. You're my best friend, it's true. Rubber Ducky, I'm awfully fond of you.
CS50. We are the Harvard Crocodillos, Harvard's oldest a cappella group, founded way back in 1946 at the historic Casey Pudding Club. We'd love to make a big thank you to CS50 staff and to David Malin for having us perform here at Sanders Theater. And if you enjoy this performance, please come audition for us this weekend at Farkas Hall.
Auditions this weekend. You can find more information on our Instagram at Radcliffe Pitches. Now, let me tell you a little bit about just about a year ago today when I was sitting in your very seats on my first day of CS50 lecture. And this is just about how I was feeling. dancing robot dog. You kind of look like you have your life together, I guess. I really need some advice. We know you're feeling unsure, but this is really the right call. In CS50, you'll meet new friends, get free food, you'll be all set for this fall. In CS50, you have 1,000 TFs here to help you. You'll get cupcakes, duckies, Chinese food. And you can always take this class as sat unsat. This is CS50, Miss Bum.
Thank you to the pitches. Cake is now served. Come up to say hi if you'd like, or meet Spot. See you next time.